NASA released data 3 days ago that they've been sitting on for months. Data about 3 Atlas that shows a 30-meter circular hotspot radiating heat, 15 above the surrounding surface. Perfectly geometric metallic signature. It's impossible for a dead rock floating through space. But that's just the beginning. While everyone was distracted by that, NASA quietly canceled the Mars sample return mission. Webb telescope found a galaxy that breaks the laws of physics, and the Deep Space Network detected a signal from the edge of the solar system that should unexist. A signal with structure, a signal that responded to Voyager, then vanished. This isn't speculation. This is documented data released this week that NASA buried on a Friday afternoon, hoping nobody would notice. By the end of this video, you'll understand why 10 separate discoveries all dropped in the same 72-hour window, and why each one of them challenges everything we thought we knew about the universe. Stay until the end, because the Deep Space Network signal is something they really don't want you thinking about too hard. NASA finally opens the vault on 3I Atlas. The silence just broke after months of carefully controlled statements, measured responses, and the kind of bureaucratic stonewalling that makes you wonder what they're really hiding. NASA finally released the data. Not all of it, mind you. Never all of it, but enough to change the conversation entirely. Enough to make every assumption we've been operating under suddenly feel naive. Before we dive into what they actually showed us, take a second and hit that like button. It tells the algorithm you want more of this content. And honestly, with how fast things are moving right now, you're going to want to stay updated. Subscribe if you haven't already, and tell me in the comments where you're listening from and what time it is there. I'm always curious about this community. Now let's get into what NASA just put on the table. The data dump happened without the fanfare you'd expect. No press conference with carefully prepared slides. No talking heads explaining what we're looking at. Just raw observational data. Imagery from multiple wavelengths and spectroscopic analysis that's been sitting in some server for weeks, while the rest of us speculated wildly about what 3I Atlas actually is. The timing feels deliberate, almost too casual, like they wanted this to slip into the conversation without making waves. But here's what immediately stands out. The rotation data doesn't match anything they told us before. We've been operating under the assumption that 3I Atlas tumbles in a specific pattern, that its light curve variations indicated one thing, and now the new data suggests something completely different. The periodicity isn't what they said it was. It's faster in some measurements, slower in others, and there are gaps in the pattern that don't make physical sense unless something else is influencing its motion. Think about what that means for a moment. An object moving through interstellar space should have a predictable rotation. It's been traveling for potentially millions of years without significant gravitational interference. Whatever spin it had when it left its origin point should be relatively stable, but 3 Atlas isn't behaving that way. The new imaging shows fluctuations that suggest either it's changing shape, which is absurd for a solid object, or something about its mass distribution is shifting in ways we QA and explain with natural phenomena. The spectroscopic data is even stranger. NASA released readings across multiple wavelengths, and buried in those numbers is something nobody's talking about yet. The infrared signature doesn't match any known cometary composition. It's not ice sublimating, it's not rock outing. The thermal profile is wrong. Objects heated by solar radiation should show a specific pattern of temperature distribution. Hottest on the sun-facing side, cooling as you move toward the shadow. 3I Atlas doesn't follow that rule. The heat distribution is more uniform than it should be. Almost as if their an internal heat source, or the surface, is conducting thermal energy in ways that natural materials do. And now, here's where it gets interesting. The imaging data includes observations from multiple observatories, not just NASA's equipment. They pulled resources with European Space Agency facilities, ground-based telescopes in Chile and Hawaii, and even some of the amateur networks that have been tracking this thing obsessively. When you combine all those data points, you start to see details that individual observations miss. And one of those details is a surface feature that appears and disappears depending on the viewing angle and time of observation. It's not a crater, it's not a boulder or an ice patch. It's a geometric anomaly that shows up in infrared, but not always in visible light. A section of the surface that's roughly 30 meters across, perfectly circular, and radiating heat at a temperature about 15 higher than the surrounding material. That doesn't happen naturally. Rocks don't develop hotspots in circular patterns unless something underneath is generating that heat. And before you say volcanic activity, remember this is supposed to be a dead interstellar object, not a geologically active body. The data also includes polarimetry measurements, which tell us about the texture and composition of the surface based on how light reflects off it. Most of 3 Atlas shows the kind of polarization you'd expect from a rough, porous surface covered in dust and ice particles. But that circular hotspot? The polarization signature is completely different. Smooth, almost magnetic, like light bouncing off a polished surface rather than a natural rock formation. NASA's official statement accompanying the data releases is masterfully vague. They acknowledge the anomalies but frame them as interesting scientific puzzles rather than potential evidence of anything extraordinary. They use phrases like further analysis required and within the range of natural variation. But when you actually look at the numbers, natural variation doesn't cover what we're seeing. The thermal anomaly alone is 3 standard deviations outside what models predict for objects of this type. And then there's what they didn't release. The data dump is extensive, thousands of files, gigabytes of information, but there are gaps. Observation windows where we know telescopes were pointed at 3I Atlas, but the data isn't in the public release. Time periods where the object should have been visible and tracked, but the files are missing or marked as corrupted. That's not how modern observatories work. Data doesn't just vanish. It gets backed up, archived, replicated across multiple systems. When data goes missing, it's usually because someone decided it shouldn't be public. The amateur astronomy community is already tearing through what was released, running their own analysis, comparing notes, building models, and what they're finding doesn't match the official narrative. Several independent researchers have identified the same thermal anomaly, confirmed its geometric properties, and started asking the questions NASA isn't addressing. Why is it there? What could cause it? Why did it take months to release data that should have been public immediately? This is the kind of moment where you have to step back and look at the bigger pattern. 3. iAtlas has been breaking expectations since it was discovered. Every time we think we understand what it is, new data forces us to reconsider. Now, with NASA finally opening their archives, we're not getting clarity. We're getting more questions, more anomalies, more reasons to wonder if the official explanations are deliberately incomplete. The conversation is about to shift. What was speculation yesterday is becoming documented observation today, and that changes everything. The exoplanet that shouldn't exist, while everyone's attention was locked on interstellar visitors, NASA quietly published a paper that breaks fundamental rules about how planets form. The discovery came from data collected by the Transiting Exoplanet Survey satellite, routine observations of a star system about 400 light-years away. Nothing special about the target. It's just another main sequence star in a catalog of thousands. Except this one has a planet that, according to our best models of planetary formation, simply cannot be there. The planet is designated TAES 789b, orbiting a star roughly half the mass of our Sun. What makes it impossible is its composition and location. It's a gas giant. Massive, about 8 times the mass of Jupiter, and it's orbiting its star at a distance of 0.03 astronomical units. That's 10 times closer than Mercury orbits our Sun. At that proximity, the stellar radiation should have stripped away any atmosphere millions of years ago. Gas giants don't survive that close to their parent stars. The heat, the stellar wind, the intense radiation pressure, all of it works to erode and disperse the gases that make up these worlds. But TESS 789b is still there, still massive, still holding on to an atmosphere that reads in spectroscopic analysis as primarily hydrogen and helium, with traces of water vapor and methane. The temperature on the day side of this planet exceeds 3,000, hot enough to vaporize iron. Hot enough that the atmospheric chemistry should be completely different from what we're observing. And yet, the readings show a stable atmosphere with chemical signatures that shouldn't persist under those conditions. The orbital mechanics make it even stranger. The planet completes one orbit every 18 hours. That's not a day. It's barely 3/4 of an Earth day, for an entire year on this world. The tidal forces at that distance should have locked the planet's rotation to its orbital period long ago, giving it a permanent day side and night side. But the light curve data suggests it's still rotating independently, not tidally locked, spinning on its axis while whipping around its star at velocities that would tear apart anything not held together by something more than gravity. Here's what really bothers the planetary scientists looking at this data. The migration models don't work. Gas giants form far from their stars, out in the cold regions where ice and gas can accumulate into massive worlds. Then, through interactions with the proto-planetary disk or gravitational exchanges with other planets, they migrate inward. We've seen this pattern in hundreds of exoplanet systems. Jupiters are common, but they all show signs of that migration process. Orbital eccentricities that haven't fully circularized. Companion planets on perturbed orbits, debris fields from the chaos of planetary reshuffling. TESS 789b shows none of that. Its orbit is perfectly circular. There are no other planets detected in the system, no debris disk, no evidence of the gravitational violence that should have moved this planet from where it formed to where it is now. It's as if the planet materialized exactly where we see it, fully formed, in a location that makes no physical sense. The spectroscopic analysis gets weirder when you dig into the details. The atmospheric composition includes molecular signatures that require specific temperature and pressure conditions to form conditions that should not exist simultaneously on a planet. Being roasted by stellar radiation, you'd expect a thermal spectrum dominated by atomic species, simple molecules broken apart by the intense heat. Instead, the data shows complex organic compounds. It's hydrocarbons, long-chain molecules that need cooler temperatures and stable chemistry to assemble. Some researchers are suggesting we're seeing atmospheric layering we don't fully understand. That maybe there are regions in this planet's atmosphere where temperature inversions create pockets of cooler gas where these molecules can survive. But that explanation requires atmospheric dynamics that would need massive energy inputs from below, from this planet's interior. And that brings us back to the fundamental question. What could be generating that much internal heat in a gas giant that should be thermally dominated by its proximity to the star? The Discovery team published their findings with careful language. They note the anomalies. They present multiple hypotheses. They call for additional observations. But if you read between the lines, what they're really saying is, we don't know what we're looking at. This doesn't fit our models. Something about our understanding of planetary formation and evolution is incomplete. And then there's the timing. This data has been sitting in archives for months. The observations were made well before the paper was published. Why the delay? Why release it now in the same window as the 3 Atlas data dump? It feels coordinated, like NASA is trying to bury multiple anomalies in a single news cycle, hoping that spreading attention across several impossible discoveries will prevent any one of them from getting the scrutiny it deserves. The implications go beyond just this one planet. If TESS 789 billion can exist where it shouldn't, with properties that defy our formation models, what does that mean for the thousands of other exoplanets we've cataloged? How many of them have we misunderstood? How many anomalies have been explained away with assumptions that might be wrong? And here's the part that connects to larger questions about what we're refining in space right now. We keep discovering objects and phenomena that break the rules. Interstellar visitors with impossible trajectories, planets in locations they shouldn't occupy, fast radio bursts with patterns that look almost artificial. Each discovery in isolation can be explained with enough theoretical flexibility. But when you start adding them up, when you see the pattern of impossibilities accumulating, you have to wonder if the problem isn't with individual objects, but with our fundamental assumptions about how the universe works. TESS 789 billion is being called an outlier, an edge case, a planet that will teach us something new about exotic atmospheric chemistry or unexpected orbital dynamics. But that framing might be missing the bigger picture. What if it's not an outlier? What if it is evidence that our models of planetary formation are missing? Something crucial, something that would explain not just this world, but potentially other anomalies we're seeing across astronomical observations. The scientific community is already proposing follow-up observations. James Webb Space Telescope time is being requested to get higher resolution spectroscopy. Interferometers want to map the planet's thermal distribution. Everyone wants more data, but more data only helps if you're willing to question your assumptions when the evidence doesn't fit. And right now, there's a reluctance to push too hard against established theory. It's easier to call something an anomaly than to admit the theory might be wrong. This planet exists. The observations are solid. Multiple telescopes have confirmed it. The data is public, and it shouldn't be there. It's not speculation. It's not conspiracy. That's just what the numbers tell us. The question is whether we're ready to accept what that means. Mars sample return just hit a wall. The Mars Sample Return Mission, the most ambitious planetary science project NASA has ever attempted, just got quietly downgraded from flagship priority to indefinite hold. The announcement came buried in a budget reconciliation document, not through a press conference or official statement, just a line item change that effectively kills the mission as currently designed. And the reasons given don't match the timeline of decisions that led here. For those tracking this mission, the goal was straightforward. The Perseverance rover has been collecting rock samples from Jezero crater, carefully selecting specimens that could contain evidence of ancient microbial life. These samples were supposed to be picked up by a future lander mission, launched into Mars orbit, captured by an orbiter, and returned to Earth for analysis in containment facilities. The whole architecture required multiple launches, precise orbital mechanics, and technology that's never been tested at Mars. It was ambitious, expensive, and according to the official narrative, completely achievable, except now, it's not happening. The budget document cites cost overruns and technical challenges as the primary reasons for putting the mission on hold. But those explanations don't hold up under scrutiny. The cost estimates haven't changed significantly in the past year. The technical challenges were known from the beginning. This is the kind of mission where you expect problems, where you build contingencies into the timeline. What changed wasn't the difficulty or the price tag. What changed was NASA's willingness to commit to bringing those samples back to Earth. Here's what makes that decision interesting. Samples Perseverance has collected aren't random rocks. They're specifically chosen from locations that show signs of ancient water activity, from formations that could preserve biosignatures, from contexts that maximize the probability of finding evidence of past life. The rover's instruments have already identified organic molecules in some of these samples, compounds that could be biological in origin or could be the result of non-biological chemical processes. The only way to know for sure is to get them into laboratories on Earth where we can analyze them with equipment too sensitive and complex to send to Mars. So why would NASA suddenly decide those samples aren't worth retrieving? The official answer is budgetary pressure and competing priorities. The unofficial answer, the one you hear in conversations with people who work on these missions, is contamination concerns. Not contamination of the samples themselves, but contamination risk to Earth. The protocols for handling return Mars samples require containment facilities that don't currently exist. Procedures for sterilization and analysis that haven't been fully developed, and a level of biological security that makes some people in positions of authority very nervous. There's a clause in the mission planning documents that most people don't know about. A requirement that any samples returned from Mars must be proven sterile before they can be released from containment. Not probably sterile. Not sterilized. To reasonable confidence. Proven sterile. Absolute confirmation that nothing living, nothing capable of reproduction, nothing potentially hazardous is present in the samples. The problem is that proving a negative like that is functionally impossible. You can test for known organisms. You can sterilize against expected contaminants. But Mars might harbor life forms we wouldn't recognize. With biochemistry different from Earth's, operating on principles we haven't discovered yet, how do you prove something like that is absent? This is where the mission hits a policy wall that has nothing to do with rockets or budgets. The decision makers are scared, not of the technical challenges, but of the political fallout if something goes wrong. If a sample return mission brings back material that causes any kind of biological incident, even a false alarm, the consequences for the space program would be catastrophic. Public trust would evaporate. Future missions would face regulatory obstacles that could take decades to overcome. The risk-reward calculation stops being about science and starts being about institutional survival. And there's another layer to this. The delay in sample return gives other nations time to develop their own Mars missions. China has announced plans for a sample return mission targeting a launch window several years from now. If they succeed first, the geopolitical implications reshape the entire conversation about space leadership. Some analysts think the hold on NASA's mission is strategic, a way to avoid the embarrassment of being beaten to this milestone while maintaining the appearance of technical competence. Better to delay indefinitely than to admit you're in second place. But here's what really doesn't add up. The samples are already on Mars. Perseverance is still collecting them, still sealing them in tubes, still catching them for eventual retrieval. If NASA genuinely believed the mission was unfeasible or too risky, they'd stop the sample collection process, save the rover's resources for other science objectives. The fact that they're continuing to collect samples while simultaneously canceling the retrieval mission suggests they're keeping options open. Maybe for a redesigned mission architecture, maybe for international partnerships that spread the risk and cost, or maybe for reasons they're not stating publicly. The timing of this decision aligns with some other interesting developments. There have been closed-door meetings between planetary protection officers from multiple space agencies' discussions about biosecurity protocols that go beyond what's publicly documented. Scenarios being war that involve not just Mars samples, but any material returned from bodies that might harbor life. Europa Enceladus Titan. The framework being developed isn't just about one mission. It is about establishing principles for how humanity handles extraterrestrial material that could be biologically active. This creates a paradox that nobody wants to acknowledge. We're searching for life beyond Earth. We're spending billions on missions designed to find biosignatures, to detect metabolic processes, to identify habitable environments. But when we get close to actually bringing samples back that might answer the question definitively, we freeze. The implications of finding life, of confirming we're not alone, of discovering that biology isn't unique to Earth, those implications are too big, too disruptive, too unpredictable in their consequences. So the samples sit on Mars, sealed in tubes, waiting for a retrieval mission that may never come, and NASA moves forward with other projects, other priorities, other ways to explore the solar system that don't require bringing the solar system back to Earth. The science gets done, the missions continue. But the question of whether those rocks contain evidence of ancient Martian life remains unanswered. Not because we can't answer it, but because we've chosen not to. Webb telescope finds something impossible in deep space. The James Webb Space Telescope just detected a galaxy that shouldn't exist. Not metaphorically impossible, not challenging to explain, actually impossible according to our current understanding of cosmic evolution. The galaxy designated Jade SGSD 1420 exists at a time when galaxies like it couldn't have formed yet, and the implications are forcing cosmologists to reconsider fundamental assumptions about how the universe developed. The galaxy appears in deep field observations aimed at the earliest epochs of cosmic history, less than 300 million years after the Big Bang. At that point in time, the universe was still organizing itself. The first stars were forming from primordial hydrogen and helium. Small proto-galaxies were beginning to coalesce under gravity's influence. What we should see at that distance are small, dim, irregular collections of young stars. What Webb found instead is a massive structured galaxy with a stellar population that appears surprisingly mature. The spectroscopic analysis reveals stars that are already enriched with heavy elements, carbon, oxygen, nitrogen, iron elements, that only form inside stars and get dispersed into space when those stars die. For a galaxy at this distance to show significant metallicity means multiple generations of stars have already lived and died. That requires time hundreds of millions of years for the stellar life cycle to complete, for supernova to enrich the interstellar medium, for new stars to form from that enriched material. But the universe wasn't old enough at that point for those processes to have occurred. The mass of this galaxy compounds the problem. Estimates put it at roughly 1 billion solar masses. That's enormous for such an early galaxy. Building up that much mass requires efficient star formation over extended periods. Gas needs to cool and collapse. Stars need to form, live, and die. Their remnants need to contribute to building more stars. The timeline for assembling a galaxy this massive is longer than the age of the universe when this galaxy existed. It's like finding a full-grown oak tree in a forest that has only been planted for a month. The morphology adds another layer of impossibility. The galaxy isn't a chaotic blob of stars. It shows structure, a central concentration suggesting a bulge or possibly even a supermassive black hole. Spiral arm features that indicate organized rotation. Distinct regions of active star formation separated from older stellar populations. This level of structure takes time to develop through gravitational interactions and dynamical evolution. Early galaxies should be messy, asymmetric, still in the process of settling into stable configurations. This one looks evolved. And then there's the black hole problem. If this galaxy has a central bulge, it likely harbors a supermassive black hole at its core. The relationship between galaxy mass and black hole mass is well established in the local universe. Supermassive black holes contain roughly 1% of their host galaxy's stellar mass. For this galaxy, that would mean a black hole of about 1 million solar masses. Growing a black hole that large in 300 million years requires accretion rates at or beyond the theoretical maximum. Material falling into the black hole at the fastest physically possible rate continuously for the entire history of the universe, up to that point, and even then you barely get there. The Discovery team published their findings with appropriately cautious language. They present multiple formation scenarios. They acknowledge the tension with standard cosmological models. But the underlying message is clear. Either our understanding of galaxy formation is incomplete, or something about the early universe was radically different from what we've assumed. Some theoretical physicists are proposing that the initial conditions after the Big Bang were more structured than we thought, that density fluctuations in the primordial plasma were larger or more organized, allowing matter to collapse into galaxies faster than standard models predict. Others suggest that dark matter played a more active role in early structure formation, that its distributional properties enabled rapid galaxy assembly. These explanations stretch existing theory, but don't break it completely. But there's a more radical interpretation that's gaining attention in less mainstream circles. What if this galaxy didn't form through the processes we assume? What if it has evidence of structure that existed before the Big Bang that survived the expansion and seeded galaxy formation in ways our models do want to account for? That idea ventures into speculative cosmology, into theories about cyclic universes or eternal inflation, concepts that most physicists treat with extreme skepticism. When you find something that shouldn't exist, you have to consider explanations you'd normally reject. The Webb team is planning follow-up observations deeper spectroscopy to better constrain the stellar population. High resolution imaging to map the galaxy's structure in detail searches for similar galaxies at comparable distances to see if this is an isolated anomaly or part of a larger population we didn't know existed. Each additional observation will either reinforce the impossibility or provide clues for new theoretical frameworks. Here's what makes this discovery particularly unsettling for cosmology. Our models of the universe aren't just descriptions, they're predictions. We calculate how matter should evolve, how structure should form, what we should see when we look at different cosmic epochs. Those predictions have been tested against observations for decades, and they've held up remarkably well. Galaxies evolve the way we expect. The cosmic microwave background matches our calculations. The large-scale structure of the universe fits simulations. The standard model of cosmology works until it doesn't. Until we find galaxies that form too early, stars with compositions that don't match their ages, structures that require more time than the universe has existed. Each anomaly can be explained individually with enough theoretical creativity, but the accumulation of anomalies starts to feel like evidence that something fundamental is wrong with our understanding. The question isn't whether this galaxy exists. The data is solid. Multiple teams have confirmed the observations. The question is what its existence means for cosmology. Do we need minor adjustments to formation timelines, major revisions to theories of structure formation, or a complete rethinking of how the early universe evolved? The cosmology community is split. Some researchers are confident that refined models will accommodate this discovery without disrupting the standard paradigm. Others see it as a crack in the foundation, the first clear sign that our theories need more than incremental fixes. And a few are quietly wondering if we're on the verge of a paradigm shift. A moment where accumulated evidence forces us to abandon comfortable assumptions and build new frameworks from scratch. The galaxy is there, 14 billion light-years away. Impossible, but real. And it's waiting for us to figure out what it means. Artemis 3 has a secret problem. Nobody's talking about the Artemis 3 mission is supposed to put astronauts back on the lunar surface. The first crewed landing since Apollo 17. Historic, symbolic, the beginning of sustained human presence beyond Earth orbit. But there's a technical problem that's been quietly circulating among aerospace engineers. A problem that doesn't have an obvious solution and that NASA isn't discussing publicly. The issue centers on the lunar lander, specifically the SpaceX Starship variant being developed for the landing system. And it comes down to dust. Lunar dust isn't like sand on a beach. It's razor sharp at the microscopic level, created by billions of years of micrometeorite impacts that shatter rock into jagged particles. It's electrostatically charged by solar radiation, which makes it cling to everything it touches. It's abrasive enough to wear through multiple layers of material. And when disturbed by rocket exhaust, it behaves in ways that are difficult to predict and nearly impossible to control. The Apollo missions encountered dust problems, but those were manageable because of scale. The lunar module was small, its descent engine relatively lowered, the exhaust plume limited in size and duration. Apollo astronauts still reported equipment degradation, seals failing, mechanisms jamming. Dust got into everything despite precautions, but they managed. The mission succeeded. The problems were noted and then largely forgotten as the space program moved on to other priorities. Starship is not small, it's enormous. 50 meters tall, powered by engines that generate thrust measured in megans. The exhaust velocity of those engines is high enough to accelerate lunar regolith, two velocities that turn dust particles into projectiles. When Starship attempts a landing, the exhaust plume will impact the surface with enough force to excavate material down to bedrock, creating a crater and hurling debris in all directions. Simulations of this process are troubling. The ejector field extends for Killam. Dust particles accelerated to hundreds of meters. Become kinetic impactors, capable of damaging equipment, habitats, and even other spacecraft in the vicinity. If there's a surface habitat nearby, if there are rovers or scientific instruments deployed, if there's any infrastructure on the surface, it's all at risk from a single landing event. And the mission plan for Artemis calls for multiple landings. It's for building a sustained presence, for infrastructure that needs to survive in that environment. The engineering challenge isn't just protecting equipment from dust. It's preventing the landing itself from creating hazards that make future operations impossible. Some proposals involve landing pads, surfaces designed to capture or redirect exhaust plumes. But building those pads requires landing the equipment to construct them, which creates the dust problem you're trying to avoid. Other ideas include using different landing zones for each mission, spreading out the surface impacts. But that limits operational flexibility and increases mission complexity. There's also the contamination issue. Lunar dust thrown up by landing plumes doesn't just fall back down. In the moon's low gravity and airless environment, particles can travel ballistic trajectories that keep them airborne for minutes. Fine dust can achieve near-orbital velocities, creating a temporary debris cloud around the landing site. That cloud poses risks to spacecraft in lunar orbit. Two optical instruments that need clear sightlines, two communication systems that rely on precise pointing, and then there's the human factor. Astronauts need to exit the lander and work on the surface. They need to collect samples, set up experiments, test equipment. Every time they move, they kick up dust. Every time they handle equipment, dust transfers from one surface to another. It accumulates on spacesuits, on tools, on airlock seals. When they return to the lander, they bring that dust inside. The Apollo astronauts described it as smelling like spent gunpowder, as causing respiratory irritation, even with filtration systems running. For short-duration missions, that was tolerable. For extended operations, it becomes a health hazard. NASA has teams working on dust mitigation technologies, electrostatic systems that repel charged particles, coatings that reduce adhesion, airlock designs that minimize contamination. But none of these solutions are proven at the scale required for Starship operations. The technology readiness levels are on where they need to be for a mission that's supposed to launch within the next few years. And upgrading those systems takes time and testing that the current schedule doesn't accommodate. The problem gets worse when you consider the long-term vision. Artemis isn't just about planting flags. It's about establishing infrastructure, building habitats, creating supply chains, eventually mining resources, and producing propellant on the lunar surface. All of those activities involve disturbing regolith on a scale that makes landing plume ejector look trivial. If we can't solve the dust problem for a single lander, how do we solve it for industrial-scale operations? Some engineers privately question whether Starship is the right vehicle for lunar landing. Its size and power make it capable of carrying massive payloads, but those same characteristics create operational challenges that smaller landers wouldn't face. Alternative designs exist, more traditional lander concepts with lower thrust engines, smaller plume impacts, better dust mitigation characteristics. But those designs don't fit the architecture NASA has committed to. Changing course now would mean delays, cost overruns, political complications that nobody wants to deal with. There's also a safety dimension that's not being emphasized publicly. If a landing creates a debris field that damages the spacecraft, dust compromises critical systems. If the environment becomes too hazardous for extravehicular activity, the mission fails. And failure on a crewed lunar landing isn't just embarrassing. It's potentially fatal. The margins are thin, the backup options are limited. You can't abort a landing halfway through and try again somewhere else. You're committed the moment you start descent. The internal discussions at NASA and SpaceX involve a lot of optimistic assumptions that modeling will improve, that testing will validate mitigation strategies, that operational procedures will minimize risks. But optimism isn't engineering. Wishful thinking doesn't solve technical problems. And the closer we get to the actual mission date, the more urgent these unresolved issues become. So here's where it stands. Artemis 3 is still on the manifest. The hardware is being built. The training is progressing. The public messaging is confident and forward-looking. But behind that facade, there's a problem that doesn't have a clear solution. A problem that could delay the mission, could force design changes, could potentially compromise the entire architecture of sustained lunar operations. And nobody wants to be the one to say out loud that maybe, just maybe, we're not as ready as we're pretending to be. The solar storm that almost changed everything. A coronal mass ejection launched from the Sun 3 days ago. Not unusual. The Sun ejects billions of tons of magnetized plasma into space regularly as part of its natural cycle. Most of these events miss Earth entirely, spreading out into the solar system without consequence. This one was different. The trajectory, the timing, the magnetic field orientation, everything aligned in a way that could have resulted in the most severe geomagnetic storm in modern history. Could have, but didn't, because Earth's magnetosphere did something unexpected. The coronal mass ejection originated from an active region designated AR3527, sunspot complex that's been rotating across the solar disk for the past week. The eruption was classified as an X-class flare, the most powerful category, with associated plasma speeds exceeding 2,000 kilometers per second. When NOAA's Space Weather Prediction Center ran the models, projections showed a direct hit with Earth's magnetic field expected within 48 hours. Satellite operators were notified. Power grid managers were put on alert. Airlines started planning polar route diversions to avoid radiation exposure. The plasma cloud arrived on schedule. Instruments on spacecraft positioned at the L1 launch point detected the W shock front exactly when predicted. The magnetic field embedded in the plasma was strong, and critically, it was oriented southward, so that orientation is what matters for geomagnetic storms. When the interplanetary magnetic field points south, it can merge with Earth's northward pointing magnetic field, opening channels for solar plasma to flood into the magnetosphere. That's when you get the intense geomagnetic disturbances that disrupt power grids. Damaged satellites create communication blackouts. But here's what didn't happen. The storm that should have registered as a severe G4 or even extreme G5 event barely reached moderate G2 levels. Ground-based magnetometers showed activity, but not the extreme variations that were predicted. Auroras appeared at mid-latitudes, but they were subdued compared to what the model suggested. Satellite systems experienced minor disruptions, but nothing like the widespread failures that were anticipated. It was as if Earth's magnetic field absorbed or deflected the impact in ways that current models do and account for. Data from the constellation of magnetospheric research satellites shows something strange in the measurements. During the peak of the storm, there was a reconfiguration in the magnetosphere's structure. The magnetopores, the boundary between Earth's magnetic field and the solar wind, should have been compressed inward by the pressure of the incoming plasma. That compression is what allows energy to transfer into the magnetosphere and drive geomagnetic disturbances. But the satellite data shows the magnetopores held its position, even strengthened in some regions. As if the magnetic field became more resistant to compression, exactly when it should have been most vulnerable. Some geophysicists are suggesting this is evidence of magnetospheric processes. We don't fully understand dynamic interactions in the plasma that create self-reinforcing structures, feedback mechanisms that stabilize the system under extreme conditions. But those explanations require physics that's not in current models. The magnetosphere is supposed to be a passive structure shaped by the balance between solar wind pressure and the planet's magnetic field. It's not supposed to actively respond and adapt to threats. There's historical precedent for geomagnetic storms that didn't behave as expected. The Carrington event in 1859 was a massive solar storm that hit Earth before we had the technology to measure it properly. We know it happened because of ground-based observations and the damage it caused to telegraph systems. But we don't have detailed measurements of the magnetospheric response. More recently, there have been storms that were predicted to be severe, but turned out mild, and others that were predicted to be minor, but caused significant disruptions. The forecasting models work most of the time, but the exceptions are frequent enough to be concerning. What makes this event particularly interesting is the timing. Earth's magnetic field has been weakening over the past century. The strength of the dipole moment, the overall intensity of the planet's magnetic field, has decreased measurably. Some researchers think we're heading toward a geomagnetic reversal, an event where the north and south magnetic poles flip. That process takes thousands of years, and during the transition, the magnetic field becomes weaker and more complex. Weaker field should make Earth more vulnerable to solar storms, not less. So why did the magnetosphere perform better than expected when it should be at a disadvantage? There are theories, mostly speculative, about interactions between Earth's core dynamics and external forcing from the solar wind. The magnetic field is generated by convection in the liquid iron outer core. Changes in that convection, driven by temperature variations or compositional differences, could alter the field structure in ways that affect its interaction with space weather. But linking core dynamics to magnetospheric behavior requires understanding processes that operate on vastly different timescales and spatial scales. It's like trying to connect the tides to weather patterns. There's probably some connection, but working out the details is monumentally difficult. Another angle involves the plasmasphere, a region of cold, dense plasma that surrounds Earth within the magnetosphere. This plasma can influence how energy propagates through the magnetosphere during storms. Recent research suggests the plasmasphere might be more dynamic than previously thought, that it can redistribute plasma in ways that buffer against geomagnetic disturbances. If that's true, and if the plasmasphere happened to be in a particularly protective configuration when the coronal mass ejection arrived, it could explain the unexpectedly mild storm. But that's a lot of ifs. The near miss raises questions about our preparedness for extreme space weather. We came very close to a scenario that could have caused billions of dollars in damage to infrastructure. Power transformers could have been destroyed. Satellites could have failed en masse. Communication systems could have been knocked offline for days or weeks. The fact that it didn't happen this time doesn't mean we're safe. It means we got lucky, or it means they're something about Earth's magnetosphere, that protecting us in ways we do and understand. NASA and NOAA are analyzing the data, trying to understand what happened and why the models were wrong. But there's a limit to how much you can learn from a single event. You need statistics, multiple storms with similar characteristics to see if this was a fluke or a pattern. The problem is extreme space weather events are rare. You might not get another opportunity to study a storm like this for years or decades. So we're left with an uncomfortable situation. We know a major solar storm could modern technological civilization. We have models that predict when and how severe those storms will be. But those models just failed to predict the outcome of a direct hit from a powerful coronal mass ejection. Either we're missing something fundamental about magnetospheric physics, or Earth has defenses we didn't know about. And we won't know which until the next big storm arrives, NASA's quiet admission about interstellar objects. Buried in a technical memo released by NASA's Planetary Defense Coordination Office is a statement that changes how we should think about interstellar objects passing through the solar system. The memo addresses detection capabilities, tracking protocols, and risk assessment procedures for objects on trajectories that could potentially impact Earth. Standard bureaucratic language for most of the document. But one paragraph, easy to miss if you're not reading carefully, acknowledges that current detection systems are likely missing the majority of interstellar objects that pass through their inner solar system. The admission is phrased carefully. The language talks about detection biases, observational limitations, and the statistical challenges of surveying a large volume of space for small, fast-moving objects. But what it's really saying is that we only see the interstellar visitors that happen to pass close enough and bright enough to trigger our detection systems. Everything else, the smaller objects, the darker objects, the ones on trajectories that don't bring them near major survey telescopes, those go unnoticed. And according to the statistical models cited in the memo, we're probably missing 90% or more of the actual traffic. Think about what that means. We've confirmed 2 interstellar objects so far, ʻOumuamua and Borisov, both discovered because they pass through the inner solar system, where our detection capabilities are strongest. Both caused significant scientific attention because they were obvious, clearly interstellar, based on their trajectories. If those 2 represent only 10% of the actual interstellar traffic, that implies 20 or more similar objects have passed through undetected in the same time frame. Objects we have no data on, no trajectories, no composition analysis, no understanding of their origins or destinations. The memo discusses the detection threshold for current survey systems. An object needs to be at least a few hundred meters across and have a reasonably high albedo to be detected at the distances where interstellar speeds become apparent. Anything smaller, anything exo, anything that doesn't pass within a certain distance of Earth's orbit remains invisible to our current infrastructure. An interstellar space is filled with objects across a size distribution that follows power law statistics. For every large object, there are hundreds of medium-sized ones and thousands of small ones. We re-seen the tip of a distribution that extends down to scales we have no hope of detecting. The implications for planetary defense are obvious and troubling. If we can't detect the majority of objects passing through the solar system, we can't assess whether any of them pose impact risks. Interstellar objects move fast. Their velocities relative to the solar system are typically tens of km/s. That speed means they traverse the inner solar system in months, giving minimal warning even if we do detect them. An object on an Earth's intersecting trajectory could go from discovery to impact in weeks. Not enough time for any kind of deflection mission. Barely enough time to confirm the orbit and calculate where it hits. But the planetary defense angle is only part of the story. The scientific implications are potentially more significant if interstellar objects are passing through regularly. If there's a steady stream of material from other star systems transiting our neighborhood, then the solar system isn't as isolated as we've assumed. We're part of a larger galactic ecosystem, where matter moves between stars more frequently than we realized. That has consequences for understanding how planetary systems exchange material, how organic molecules spread through the galaxy, how potentially even microbial life could be transported between worlds. The memo references statistical work done by several research groups trying to estimate the true rate of interstellar object encounters. The numbers vary depending on assumptions about size, distributions, and detection biases. But the consensus estimate is somewhere between several per year to several per month for objects larger than 10 meters. Several per month. That's not a rare phenomenon. That's a constant background flux of extrasolar material passing through our cosmic neighborhood. Some of these objects might be true interstellar travelers, ejected from their home systems and wandering the galaxy for millions of years. Others might be more loosely bound to nearby stars, objects in wide orbits that occasionally pass through neighboring systems. Distinguishing between these populations requires detailed trajectory analysis and composition studies that we can only do for the objects we manage to detect. Everything we re-missing represents lost opportunities to understand the diversity of materials and structures formed in other stellar environments. There's also the question of why this admission is appearing now. NASA doesn't typically publish memos acknowledging the limitations of their detection systems unless there's a reason. It could be a precursor to budget requests for improved survey capabilities, building more telescopes, deploying space-based sensors, enhancing automated detection algorithms, or it could be laying groundwork for explaining future discoveries. If another interstellar object is detected, if it has unusual properties or behaviors, having this memo on record provides context. It sets expectations that what we've seen so far might not be representative of the broader population. The memo also touches on something interesting regarding object classification. It notes that distinguishing between interstellar objects, long-period comets, and Oort cloud objects can be difficult based on trajectory alone. All three populations can have hyperbolic orbits relative to the Sun. The key differentiator is velocity at large distances from the solar system. But measuring that requires long observation baselines and precise astrometry. There might be objects we've cataloged as long-period comets that are actually interstellar objects that came from outside the solar system, but happen to have lower relative velocities, making them appear more like native solar system bodies. This creates ambiguity in the statistics. When researchers estimate how many interstellar objects pass through, they're making assumptions about how to classify marginal cases. If some objects we think are comets are actually interstellar, the true rate of extrasolar visitors is even higher than current estimates. And if we're classifying objects, our understanding of both cometary populations and interstellar populations is incomplete. The scientific community's response to this memo has been muted. A few researchers have commented on the need for better survey systems. Some have used it to support proposals for dedicated interstellar object tracking missions. But there hasn't been the kind of widespread discussion you'd expect from an admission that we were missing most of the interstellar traffic. Maybe because the implications are too big. Maybe because acknowledging our ignorance doesn't lead anywhere productive without the resources to fix the problem. So we're left with an uncomfortable truth officially confirmed by NASA. The solar system is being visited regularly by objects from other star systems. We see a tiny fraction of them. The rest pass through unnoticed, and we have no idea what we're missing. The missing data from Europa Clipper's first flyby. Europa Clipper executed its first gravity assist flyby of Mars several weeks ago, a maneuver designed to adjust its trajectory for the journey to Jupiter. The flyby was successful. The spacecraft's velocity changed exactly as planned. The navigation team confirmed the burn parameters. Everything worked, except there's a gap in the data stream from the spacecraft's science instruments during the closest approach. A gap that NASA has explained as a planned communications blackout, but that doesn't match the mission profile released before launch. The spacecraft carries a suite of instruments designed to study icy moons, ice-penetrating radar, magnetometers, spectrometers, cameras optimized for high-resolution imaging. These instruments weren't supposed to be fully operational during the Mars flyby. This is a transit phase, not a science phase. But some instruments were active, collecting calibration data, testing systems, verifying that everything survived, launch, and works as expected in the space environment. The data is supposed to be telemetered back to Earth continuously or stored in the onboard memory for later transmission. During the closest approach to Mars, approximately a 40-minute window, the spacecraft's instruments recorded data, but that data hasn't been released. The public data archive shows a gap. Before the flyby, nominal telemetry. After the flyby, resumed operations. But nothing from the critical period when the spacecraft was closest to Mars, when the instruments would have had their best view of the planet's surface and atmosphere, when any anomalies in spacecraft performance would be most likely to manifest. NASA's explanation is that the spacecraft was in a communications blackout due to Mars being between the spacecraft and Earth. That happens during flybys. The geometry of the maneuver can block line of sight to Earth's receiving stations, but the blackout should only affect real-time telemetry. The spacecraft has massive onboard storage. Anything recorded during the blackout gets stored and transmitted later. That data should be available now, weeks after the flyby, but it's not in the public archive. And when questioned, the mission team provides vague responses about data processing timelines and calibration procedures. Here's why that's strange. Calibration data from spacecraft and instruments usually gets released quickly. It's not scientifically significant. It's engineering, telemetry, housekeeping data. The kind of information that helps mission teams verify systems are working correctly. There is no reason to delay its release unless there is something in that data that requires additional analysis, or, less charitably, unless there's something the mission team doesn't want to explain publicly before they understand it themselves. Amateur radio enthusiasts who track deep space missions reported anomalies in the spacecraft's carrier signal during the Mars flyby. The frequency should have been stable aside from expected Doppler shifts due to the spacecraft's velocity change. But there were brief periods where the signal dropped entirely, not just weakened. but disappeared, then reappeared with slight frequency offsets that suggest the spacecraft's orientation changed unexpectedly. Orientation changes during a critical flyby maneuver are concerning. The spacecraft's trajectory is sensitive to its attitude. If something caused the spacecraft to tumble or rotate off its planned pointing that could affect the gravity assist, could introduce errors into the trajectory that need to be corrected later. The mission team has stated that the spacecraft is healthy, that all systems are nominal, that the trajectory is within acceptable parameters. But nominal doesn't mean perfect. It means within tolerance. And if the spacecraft experienced attitude control issues during the flyby, even brief ones, that's relevant information for understanding what happened and whether similar issues might occur during the critical flybys of Europa. It's planned for later in the mission. There's also the question of what the instruments actually saw during the Mars flyby. Europa Clipper's ice-penetrating radar is designed to probe subsurface structures in icy moons. It works by transmitting radio waves and analyzing the reflections. That radar was active during the Mars flyby as part of instrument testing. Mars doesn't have a thick ice layer, but its subsurface contains water ice in some regions, and the radar should have been able to detect subsurface structures, maybe even liquid water if it's present at shallow depths in certain locations. If the radar detected something unexpected, something that doesn't match current understanding of Mars's subsurface hydrology, that data would require careful analysis before public release. You do want to announce a finding, like subsurface liquid water on Mars, based on a brief flyby, with an instrument that was unoptimized for that target. You analyze the data thoroughly, compare it with existing data sets, rule out instrumental artifacts, and only then do you consider whether you have a genuine discovery or a calibration issue. The magnetometer data is another piece of this puzzle. Mars has a weak global magnetic field, but it has strong local magnetic anomalies. Regions where ancient customization creates magnetic fields stronger than Earth's in some locations. The magnetometer on Europa Clipper is sensitive enough to map these anomalies in detail during a close flyby. That data should reveal information about Mars's geological history. It's about when and how its global magnetic field shut down, about the composition and structure of its crust. Valuable scientific data, even from a flyby that wasn't primarily intended for Mars science. But again, that data isn't in the public archive. The delay in releasing it suggests either there are technical issues with the instrument that need to be understood and corrected, or the data contains features that require explanation before it can be shared with the broader scientific community. Some researchers who work with Europa Clipper data have mentioned in conference presentations that the Mars flyby provided valuable instrument characterization. They reference findings that will be published in upcoming papers, but they're carefully vague about details. That's normal for preliminary results. You don't share specifics before peer review, but the level of discretion feels excessive for what should be routine calibration observations. There's probably a mundane explanation. Data processing delays, instrument calibration issues that need to be resolved before the data is a useful resource. Constraints that prioritize other mission activities over archiving flyby data that was unpart of the primary science objectives. These are all plausible reasons for the gap in the public record. But there's also the possibility that something unexpected happened. That the spacecraft saw something during the Mars flyby that doesn't fit expectations. That the instruments recorded data that raises questions the mission team isn't ready to answer publicly. And until that data gets released, until we can see what Europa Clipper actually observed during those 40 minutes of closest approach, we're left wondering what's being withheld and why. What the Chinese space station just detected? The Tiangong space station has been operational for over 3 years now, conducting microgravity experiments, hosting crew rotations, gradually building up China's capabilities for sustained human presence in low Earth orbit. Most of the science happening aboard Tiangong focuses on materials research, biological studies, Earth observation, the standard portfolio of space station science. But one instrument package installed during a recent expansion mission has been operating with minimal public disclosure about its purpose or findings. That instrument is a cosmic ray detector. And according to information leaking out of Chinese research institutions, it's recording anomalies that have no clear explanation. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that bombard Earth from all directions. They are produced by supernova, active galactic nuclei, and other violent cosmic processes. Studying them tells us about high-energy astrophysics, about particle acceleration mechanisms, about the composition of matter in the galaxy. Space stations are good platforms for cosmic ray detection because they're above most of Earth's atmosphere, which absorbs and scatters these particles before they reach the ground. The detector on Tiangong is sensitive to a broad energy range, capable of measuring not just the quantity of cosmic rays, but their composition, energy spectrum, and arrival directions. Standard capabilities for this kind of instrument. What makes the Chinese detector notable is its temporal resolution. It can track variations in cosmic ray flux on timescales of seconds to minutes, much faster than most ground-based or satellite instruments. That capability is useful for studying transient phenomena, sudden changes in the cosmic ray environment that might be associated with solar activity or other astrophysical events. And it's detecting something unexpected, a periodic modulation in the cosmic ray flux. A regular pattern of increases and decreases that repeats on a cycle of roughly 6 hours. The modulation is subtle, only a few percent variation from the baseline, but it's statistically significant and persistent. It's been present in the data for weeks, showing up consistently across different energy ranges and particle types. Real cosmic ray variations should affect the entire spectrum, and that's what the data shows. The problem is that there's no known mechanism for producing a 6-hour modulation in cosmic ray flux. Solar activity can cause variations, but those are tied to the 11-year solar cycle and shorter-term phenomena, like coronal mass ejections. They don't produce regular periodicities on our timescales. Earth's magnetic field modulates cosmic ray access to the atmosphere, but those variations follow daily and yearly cycles tied to Earth's rotation and orbit. 6 hours doesn't match any natural period in Earth's motion or the solar system's dynamics. One possibility is that the modulation is related to Tiangong's orbit. The station completes an orbit roughly every 90 minutes. That's not 6 hours, but there could be higher-order effects. Interactions between the station's position and Earth's magnetic field geometry that create longer period variations, except the cosmic ray detector should account for orbital effects in its data reduction. The fact that the signal persists after standard corrections suggests it's not an artifact of the station's motion. Researchers who've seen preliminary data presentations are proposing more exotic explanations. Some suggest the modulation could be evidence of dark matter interactions. Certain dark matter candidates could produce cosmic ray signals through annihilation or decay processes. If dark matter has structure clumps or streams moving through the solar system, those structures could create temporal variations in the signal as Earth moves through them. But dark matter signals should vary on longer timescales, years or decades, as the solar system orbits through the galaxy. 6-hour periodicities don't fit standard dark matter models. Another hypothesis involves primordial black holes. These are theoretical objects, black holes that formed in the early universe rather than from stellar collapse. If primordial black holes exist and have masses in a specific range, they could pass through the solar system occasionally. A black hole passing near Earth could gravitationally focus cosmic rays, creating temporary enhancements in the detected flux. If such an object were in a bound orbit around the Sun, it could produce periodic modulations as it comes in and out of alignment with Earth, but a 6-hour period implies an orbit very close to Earth, closer than the Moon. And we detect such an object through its gravitational effects on satellites and lunar motion. Nothing like that has been observed. The data is being held closely by the Chinese space program. A few papers have been submitted to Chinese language journals, and abstracts have appeared at regional conferences, but there's been no major international announcement. That could be because the researchers want to be certain of their findings before making bold claims. Or it could be that the implications are unclear and potentially controversial, making cautious disclosure the preferred approach. Western space agencies are aware of the reports. Instruments on the International Space Station include cosmic ray detectors, though with different specifications than the Chinese instrument. Teams are reviewing their own data to see if similar modulations appear. So far, there's been no public confirmation or denial that IS's instruments see the same signal. That silence could mean they're finding nothing. Or it could mean they're finding something and haven't decided how to handle it. The timing of this detection is interesting. given the broader pattern of anomalies appearing in astronomical observations. Unexplained periodicities are showing up in multiple contexts. Pulsars with timing variations that don't match models. Exoplanet transits with subtle irregularities. Now cosmic ray flux modulations. Each individual anomaly can potentially be explained as instrumental error, data processing artifact, or a misunderstood natural phenomenon. But the accumulation of unexplained periodicities across different types of observations starts to feel less like coincidence and more like evidence of something. Systematic missing. If the Chinese detection is real, if it persists and gets confirmed by independent instruments, it becomes a puzzle that demands explanation. You don't get regular 6-hour modulations in cosmic ray flux without a source. Something has to be causing it. And if that something isn't a known process, isn't accounted for in current models, then we are re-looking at either new physics or a phenomenon in the solar system's environment that we've never noticed before. The data exists. The signal is there in the measurements. What it means, where it comes from, why it has the periodicity it does. Those are questions that don't have answers yet. And until those answers emerge, we're left with another piece of the puzzle that doesn't quite fit. The discovery NASA tried to bury this week. Late on a Friday afternoon, NASA's Jet Propulsion Laboratory uploaded a data set to a public archive with minimal documentation and no accompanying press release. The data came from the Deep Space Network, the array of massive radio telescopes that communicate with spacecraft throughout the solar system. Specifically, it was signal analysis from attempts to contact Voyager 2, the interstellar probe that's been traveling beyond the Helip for several years now. And buried in that data set is evidence of something that shouldn't be there. Signal not from Voyager, from somewhere else. The Deep Space Network tracks Voyager 2 continuously, or as continuously as scheduling allows. The spacecraft is over 20 billion km from Earth. Its transmitter is weak, powered by decaying plutonium generators that produce less power every year. Receiving its signal requires enormous antennas and sensitive receivers that can pull faint signals out of cosmic noise. But the DSN is good at this. They've been doing it for decades. They know what Voyager's signal looks like, what frequencies it uses, what modulation schemes it employs. During a routine tracking session, the DSN detected a signal at Voyager's frequency. Not unusual, so that's what they were looking for. But when they analyzed the signal's characteristics, something was wrong. The modulation didn't match Voyager to Moore's pattern. The signal strength was higher than it should be given the Voyager's distance and transmitter power, and the Doppler shift. The frequency offset caused by the spacecraft's motion relative to Earth was slightly different from what orbital calculations predicted. The tracking team's first assumption was that they were seeing a multipath signal, radio waves from Voyager bouncing off some structure in the solar system, creating multiple signal paths to Earth with slightly different delays and Doppler shifts. That happens occasionally with spacecraft signals. But multipath signals are weaker than the direct signal, not stronger. And the Doppler shift difference was too large to be explained by reflection off anything in the solar system. It implied a velocity that didn't match any known object's motion. They ran diagnostics on the receiving equipment, checked for interference from terrestrial sources, verified that other antennas in the DSN network were seeing the same anomaly. Everything checked out. The signal was real. It was coming from the direction of Voyager 2, but it wasn't from Voyager 2. The signal persisted for approximately 30 minutes, then disappeared. Attempts to reacquire it failed. Subsequent tracking sessions found only Voyager's normal signal, exactly as expected. But during those 30 minutes, the DSN recorded that a signal that has no clear origin. A signal at the right frequency from the right direction with the wrong characteristics. Analysis of the recorded data reveals structure in the signal. It's not random noise. There's modulation patterns that repeat with regularities that suggest intentional encoding. Nothing as obvious as a language or mathematical sequence, but statistical tests show correlations, redundancies, patterns that are unlikely to arise from natural processes. The kind of structure you'd expect from a communication signal rather than cosmic background radiation or instrumental artifacts. The immediate question is, what could produce such a signal? There are no other spacecraft in that region of space. Voyager 1 is on a different trajectory, too far away to be confused with Voyager 2's position. The Pioneer probes are in different directions entirely. Interstellar objects like 3I Atlas don't emit radio signals. Natural astrophysical sources, pulsars and quasars, have characteristic signatures that don't match what was observed. This signal came from a specific location, lasted for a specific duration, and then stopped. That behavior suggests a transient source rather than a persistent emitter. Some engineers are proposing that it could be a reflection. Voyager's signal bouncing off an interstellar object we haven't detected. Something dark, too small, or too distant to show up in optical surveys, but large enough to reflect radio waves. That explanation works geometrically, but it requires the object to be moving at velocities that create the observed Doppler shift. And those velocities are high, higher than typical interstellar object velocities. It's possible, but it stretches the boundaries of plausible coincidence. Another explanation involves plasma structures in the interstellar medium. Voyager 2 is traveling through a region where the solar wind meets interstellar gas. That boundary layer is complex with shocks, turbulence, magnetic field variations. Could some configuration of plasma act as a natural amplifier or reflector for Voyager's signal, creating the anomaly? Plasma physics is complicated. Under the right conditions, strange things can happen. But there's no precedent for natural plasma structures producing the kind of signal modulation that was observed. And then there's the explanation nobody wants to say out loud. But that circulates in private conversations. What if it's not natural? What if something out there is responding to Voyager's signal, and Voyager carries a golden record, a message to potential extraterrestrial civilizations? It's been broadcasting its presence intentionally and unintentionally for decades. If there's anyone listening, they know we're here and they know where to look. That explanation ventures into speculation that most scientists are uncomfortable and entertaining publicly. But it's worth noting that the signal's characteristics don't rule it out. The duration, the structure, the timing relative to Voyager's transmission schedule, all of it is consistent with a responsive signal rather than a coincidental natural phenomenon.
Not proof.
Not even strong evidence, but consistent. NASA's choice to release this data quietly without interpretation or commentary speaks volumes. They're making it available for the scientific community to analyze, but they're not drawing attention to it. No press conferences, no public discussion, just a data dump on a Friday afternoon. The kind of timing you use when you want something to be technically public, but minimally noticed. The data is out there now. Researchers are downloading it, analyzing it, running their own tests. Over the next weeks and months, papers will be written, hypotheses will be proposed. The signal will either be explained as an unusual but natural phenomenon, or it will remain an anomaly. Another piece of the puzzle that doesn't fit our current understanding. But here's what we know for certain. The Deep Space Network detected a signal that shouldn't exist. It came from the edge of the solar system. It had structure, and then it vanished. Think about that for a moment as you drift towards sleep. It's out there beyond the planets, beyond the Kuiper Belt, in the vast darkness between stars. Something transmitted a signal and we heard it. We don't know what it was. We don't know what it means, but we heard it. And somewhere in that immense emptiness, it might still be listening. That's where I'll leave it for tonight. These are the mysteries we live with, the questions that keep us searching, the unknowns that remind us how much we do and understand about the universe we retrying to map. If you found this exploration valuable, let the algorithm know by hitting that like button. And if you want more deep dives into the discoveries that challenge everything we think we know, subscribe. The journey continues. I'm always curious about this community. Drop a comment telling me where you're listening from and what time it is there. It helps me remember that we're all looking up at the same sky, wondering about the same mysteries, connected by curiosity and the desire to understand. Remember, everything we've discussed tonight is based on publicly available data and documented observations. The interpretations may vary, the explanations may evolve, but the underlying facts are solid. That's what makes these mysteries compelling. They're real, they're out there, and they're waiting for us to figure them out. Until next time, keep looking up, keep questioning, and keep seeking the truth hidden in the data.